Hello everyone, and welcome to Transfer of Energy in an Ecosystem. So this is what we're asking today. Why do organisms need energy? And the answers are growth, movement, repair and maintenance, and reproduction. Things we need to be classified as a living thing. So energy is transferred from the sun to autotrophs, and then to organisms that eat those autotrophs. Then to organisms that feed on other organisms. So we look at the sun will go to plants, and then the plants will go to organisms that eat plants, and then from there, animals that eat other animals. So we have the laws of thermodynamics, and the laws of thermodynamics, there's two of them. We have the first law, which is the law of conservation of energy, and this says that energy can neither be created or destroyed. However, it can be transformed from one to another. So how this generally happens is we transfer from potential energy to kinetic energy, and then that kinetic energy or potential energy can be transformed into different types of energy, like chemical energy or heat. And when we're losing heat, all we're doing is we're giving off energy. The second law of thermodynamics is whenever energy is converted from one form or another, some usable energy is degraded into heat, which is a less usable form, and it disperses into the environment. So energy is never transferred at 100%. So due to the low rate of energy transfer, it explains why ecosystems rarely have more than a few trophic levels. There's just not enough energy at the top level to support more. Organisms at the lowest trophic level are the most abundant than those at the highest level because higher trophic levels contain less energy, so they support fewer individuals. So here, our example is that there's about 1,000 zebra gazelles and other herbivores for every lion you see. And there's far more grass, shrubs, and herbivores. So here's the neat thing about this. When we transfer energy, we only transfer 10%. So if we had 1,000 energy, then this zebra is getting 100, and then this lion is only getting 10. In living things, energy is transferred as organic matter, and this may be described as food. It might be described as carbohydrates, as glucose, as fats, as starch. Carbs and starch are essentially very similar. They are a bunch of glucose molecules lined up and attached together. And it is one of the more quick, usable forms of energy. So if you ever hear a runner right before a run, the day before, they're going to be carbo loading. They're going to be eating a lot of carbohydrates, which means that's that quick energy that they can use during the race to chop up and get that energy from. Fats are a long-term source of energy, and those fats are uh, something that's stored, and then later on when you need it, you can break it down and use it later. And then there's two other biomolecules that we'll go over later. So biomass, this is the amount of living matter or tissue in a given habitat. So here we have producers. These can only harvest 1% of the sun's energy, and they are photosynthetic and make most carbohydrates by using energy of the sun. They are known as autotrophs because they make their own food. Auto means self, troph means to eat, so it's an autotroph. It makes its own food. In terrestrial ecosystems, plants are our major producers, where in aquatic, it's your photosynthetic protists and bacteria that are our major producers. Chemosynthesis. This is using bacteria using energy stored in inorganic molecules, such as hydrogen sulfide or hydrogen sulfate, to produce carbohydrates. So you get these hydrogen sulfate through these hypothermal vents over here. And this is important because the bacteria is going to use that hydrogen sulfide like plants use carbon dioxide. So measuring productivity, we do this by the gross primary productivity. It is the rate at which a producer in an ecosystem can capture the energy of sunlight by producing organic compounds, or photosynthesis. The rate at which the biomass accumulates is called the net primary productivity, or the NPP. So our net primary productivity is going to equal the gross primary productivity minus cellular respiration. The NPP is what's available to move up the food chain. Here's our different types of ecosystems. If you remember from the last, from 18-1 notes, we talked about estuaries, swamps and marshes, tropical rainforests. But in this lovely little graph that we have the average net primary productivity. So kilocalories per meter squared per year. So we can see that estuaries, swamps and marshes, and tropical rainforest produce the most, where extreme deserts produce the least. Consumers. They obtain energy by eating other organisms. This include herbivores, omnivores, carnivores, detritivores, and decomposers. They are also known as heterotrophs. They do not make their own food, they eat others to get their food. So a decomposer, they're very important because they make nutrients that were contained in dead plant or animal organic matter, and waste, detritus, available, and it makes waste, which is detritus, available again to the autotrophs in the ecosystem. So our decomposers are fungi, bacteria, and worms. And they put nutrients back into the soil. So some food chains and food webs. A food chain is a single pathway of energy transfer. So right here, this is a food chain. A food web would be showing all paths of energy transfer. So when an organism eats another organism, molecules are metabolized and energy is transferred, and only 10% is moved up to the next animal, to the next consumer. I'm going to start. Boop. So a food chain will show us all paths of energy from one living thing to another. And decomposers like bacteria are necessary for all food chains. So the reason why we're not showing a decomposer here is because all of these would have an arrow going to the decomposer. Now the big thing I want you to see with this is the arrow goes from the one who's making to the one who's eating it. So from the plant to the insect. From the insect to the mouse. So the mouse is eating the insect. So the insect is giving energy to the mouse. So here we have a food chain of an Antarctic ecosystem. We have the algae going to the krill, krill going to the cod, cod to the leper seal to the killer whale. So here we have a food web. If we look, the food web shows all the different interacting bits and who eats who. Trophic levels. One way to follow a pattern of energy flow is to group organisms in an ecosystem based on how they obtain energy. So here at the bottom, the first trophic level is producers. And it makes the most energy. So there's a lot of them. And then we go to the herbivores. There's a lot more, but there's not as many. If you look, it looks maybe about 10%. then you go to the small carnivores, and then you go to the large carnivores. And an organism's trophic level indicates their position in a sequence of energy transfers. A large carnivore is going to be like the fourth in the trophic level. It needs to eat something that ate a producer. Ecosystems contain only a few trophic levels because what happens is if we have something that eats a large carnivore, it's going to get so low of an energy rate that it's going to need to eat something else that's much more nutritious. And it's going to give him much more energy. 10% of transfer. Some organisms are not eaten, so when an organism is eaten, the consumer can't always break down all the organism's molecules. This is why we only get 10%. A cougar, or humans, cannot extract energy from the antlers, hooves, and hair of a deer. It's not what we eat because we can't break it down. And because we can't break it down, we can't get that energy from it. Now, if we were able to eat all of it and everything, then we might have gotten some of the energy. But you got to remember, energy is lost due to heat. It's not destroyed, it's just transferred into heat. The energy the prey used for cellular respiration can't be used to make new biomass. That was used for growth, repair, maintenance of the organism. So in other words, we can't use all the energy harvest from the GPP. Only the NPP is available. So we have no transformation of energy being ever 100% efficient. It's the second law of thermodynamics. We lose energy as heat. And when we eat things when we eat other animals, that energy that was lost as heat, we can't get that. That's not part of the NPP. So is it better to eat lower on the food chain? Being a vegetarian rather than a meat eater decreases a person's ecological footprint. And each amount of meat or animal product that we eat requires an input of considerably greater amount of plant material. However, the thing with this is, do we get all the things we need by eating only plants? So there's a question for you. Think about it and bring it to class next time. Biomagnification. So this is what happens to a toxin as it moves up the food chain. So here, this is mercury concentration. So we get some mercury in the water. The plankton are going to eat a little bit of the mercury. Well, the aquatic insects, to get as much energy as the plankton does, needs to eat quite a bit of plankton. So if the plankton had only one concentration, the aquatic insect needs to eat, like, let's say it needs to eat 3 to get its daily nutrient value. So that one that was in the plankton, well, it just ate 3 plankton. So now that one aquatic insect has 3 mercury. So I'm going to do this. Okay, so there's 1 per plankton here. The aquatic insect needs to eat 3. So there's 3 in each aquatic insect. So we're going to say each of them are going to eat 3. So if this insect-eating fish needs to eat the aquatic insect, well, that's 3 times 3, that's 9. That's 9 mercury in that one. This fish-eating fish, it needs to eat 3 of these insect-eating fish. Well, 3 times 9 is 27. And the human will need to eat 3 fish-eating fish. So look at how that went. It just grew from there. There you go. So that's biomagnification. It just magnified. It just grew exponentially. So there's 3 different types of pyramids. We have a pyramid of numbers. So we have grass being the biggest, rabbits being more, and then a fox being the smallest. Here we have another one for an aquatic one. We have phytoplankton. Not as much phytoplankton as zooplankton. Zooplankton's a lot more. But then you have herring. A lot less herring. There is more phytoplankton and zooplankton than there is herring. And same with the sea lions. Then you have the pyramid of biomass, so how much biomass is there of it. Very similar for both, very similar for pyramids of numbers and pyramids of biomass. Then we get the pyramid of energy. And the grass, while it's getting only 1% of the sun's energy, has a lot more energy than the fox or the rabbit. So the fox needs to eat a lot of rabbits, and the rabbits needs to eat a lot of grass to get the same energy. And if we look at where the phytoplankton is, the phytoplankton, because it's getting the sun's energy, it's not losing any energy by eating anything else. It's getting its energy directly from the sun. It has a lot more. Zooplankton eats phytoplankton. Phyto meaning light, zoo meaning animal. So the zooplankton is an animal plankton. It's going to eat phytoplankton. So this is where this becomes different than these two.